Hello there, exercise 8A. We're doing exponential graphs and we're looking at the shape and the properties of these exponential graphs and making sure that we are able to draw them, I suppose, and understand them. And we've touched on this before. Before I go any further, let's remind us, a little starter, what these graphs are meant to look like. So you should be able to just sketch these straight off. So pause the video for about 30 seconds and I reckon you should have been able to draw them by then. So at least some of them you should have known off by heart. So this first one, y equals x squared, you should know basically the U-shaped graph. And that's what it looks like. I would be thinking, what do I need to draw in the exam? I definitely need to draw that kind of shape. But because it crosses only in one place and it crosses at the origin, that's probably it. That's all I need. So y equals x squared. Next one, y equals x cubed. Again, what am I thinking I need is a very minimum. I should know it starts low, curves round, touches there, and then curves round. So the only place it hits is the origin, and that's the graph of y equals x cubed. Now, what does it look like? The official version is that y equals x cubed. Now, 1 over x, you should know, really comes in two parts. You might have only known one part of it. You might have known that there's a part here. There's also a part there, the negative part. So officially it looks like this. It doesn't cross the axis anywhere. So notice mine is very much, there's a gap between these. And if it was me, I'd be showing these axes, but making sure that I leave a gap here and here. And here it just about, yeah, you can just about see there is a gap there. But if you're not careful on your calculator, it very quickly touches. And so I wouldn't want you to show it touching. You'd want to show the gap. This next one, I've had other people describe it over the years as curtains. It looks like this. It's probably not one you've seen before. So it looks something like that. I don't know why it's starting to curl up, which it shouldn't do. So there's my y-axis. There's my x-axis. And it's getting closer and closer. And that's the official version of it, y equals x squared. 1 over x squared, that is. So there's 4 graphs that we're meant to know. Notice that I've described these as standard graphs, graphs that you're meant to recognize and go, I know what that looks like. So for instance, if I then said y equals x squared plus 4 equals, it's a bit higher up. Translation has occurred. So anyway, all functions of the form y equals a to the x are called exponential functions. I don't know, I've written it twice. Y equals 2 to the x then. It looks like this. That's why, because I had the graph. So notice this graph crosses here at 1. This is a very important aspect of these. All these standard graphs cross at 1. So just bear that in mind. Notice again, it doesn't really mean to, or isn't meant to touch it. Obviously the gaps get smaller and smaller to the point where you can't see the gap anymore. But you should try to leave your graph. If I was drawing this on my graph, I'd be going, it looks something like that. Crosses at 1. Definite gap here. So that's the graph anyway, and these are called exponential functions, and sometimes this would be described as an exponential growth function. Here are 3 different types of it. Y equals 4tx, y equals 3tx, y equals 2tx. Notice they all cross at 1. Interestingly, the one at the bottom here, y equals 2tx, and then there's y equals 3tx, y equals 4tx. So as you get the higher numbers, it goes upwards, and you wouldn't be surprised at that 2tx compared to 3tx compared to 4tx. But notice on the other side, actually 2tx is the highest one, and then 3tx, and then 4tx. The bigger the number, the more it gets closer to this x-axis, or at least the quicker it does. So there are 3 different graphs, and again, the higher the value of a, then the steeper the graph on this right hand side, and the lower on this side. Still all crossing at 1, and that's basically because if you put any number to the power of 0, and of course this coordinate here is the coordinate 0, 1, so the x value here is 0. So if I do a to the 0, it's 1. So it doesn't matter what value it is. Here, these are exponential growth functions. This is an exponential decay function. And it's exponential decay because you can see it going down, down, down. So how do we get that? Notice it's y equals 0.5 to the x. So that implies that if you have a value of a between 0 and 1, when we do our y equals a to the x graph, if you've got a value here for the a between 0 and 1, it's going to go down like this does. So 0.5 to the x looks like this. Now, again, I've drawn lots of different types on here. This is y equals 0.1 to the x, 0.3 to the x, 0.5 to the x, 0.7 to the x. And again, goes kind of the wrong way, I suppose. The steeper is the smaller the number, the flatter it is, then it really is, 0.7 to the x is almost flat, isn't it? You can see it just looks like a straight line. It's not a straight line. It is a curve, which will eventually curve up like this, but it takes a long time to do it. If you ever did the y equals 1 to the x, well, that's actually just a dotted line going straight, or not a dotted line, a straight line going straight across. Again, all hidden at 1, notice. But now they are going down. And so what we're really saying is if it's y equals a number bigger than 1, it will go upwards like this. If it's y equals 1 to the x, it will just go straight across. Any number lower than 1 actually starts coming down again. You can see it's quite nice the way it does that. So this might be the y equals 2 to the x, 3 to the x, whatever I've said before. So numbers of more than 1 go up, the exponential growth. If it was 1, it would go straight across. If it's less than 1, it starts going down. And very small numbers go steeply down. So that's exponential decay. Notice, by the way, it's not possible for a to be less than 0. So you won't get a graph which is y equals, say, minus 2 to the power of x. And if you ever think about that, you might understand why, but you won't get it. You won't see it, so most of you won't care. But maybe ever think about why. The function e to the x is a funny old function. We already have seen certain funny numbers like pi, and we've seen this even before. When we were doing logarithms, we were told that this natural logarithm can be written if we wanted to as log to the base e, and this e is a funny old number. So if we just have a look for a moment of this graph, y equals e to the x, it's still crossing at 1, still looking very much the same as the others. It's a number, it's a weird number actually. Y equals 2.718 to the x is an alternative way of writing it. 2.718 is not a made up number, it is a very definite number. And I suppose this is starting to look at the reasons why. So if we look at the gradient of these graphs, now the red one is the actual graph. This is y equals 2 to the x. And if you look at the gradient here, for instance, here it's positive, here it's a bit less positive. And so what you can get the computer to do, you can say to it, find the gradient of all these different points. So it finds the gradient of this point here, and it said it's got a value. Now you've got to take my word for this. So it says at this point here, the gradient has a value of about 1.6-ish. And you go, okay, fair enough, if that's what you say. Here, I'm telling you the computer has told me the gradient is not so steep. So it's about looks about 0.8-ish there. And I know that because it's plotted it at 0.8. At this point, it's got a gradient of about 0.4. And you'll notice for all these points, you can work out the gradient. And you can plot a graph of all those points. And it's quite amazing, really, because the graph is very similar to the first graph. This is y equals 2 to the x, but this one doesn't seem as steep, so it must be y equals, I don't know, 1.5 to the x or something. I don't know. I have no idea what that is, but it's of the same type of form in terms of it's an exponential graph. You can see it looks very similar, just not so steep. And I suppose it's not even quite the same because it can't be 1.5x because it's definitely moved down. It's not crossing at 1. So it's not that. It's something though. It's related to it, you would think. This is y equals 3 to the x. So again, the red one is y equals 3 to the x. And when you draw its derivative graph, you can see actually it's very, very similar to the red graph. Its gradient at any point is a little bit too big. But it's fair play to it. It's very, very similar to the original graph. What exactly it is, it's open for debate, really. And the next obvious thing to do then, I suppose, is to think of the next graph, which is y equals 4 to the x. And you'll notice on y equals 4 to the x, it's even steeper. Now, it's a slightly different scale on this one, just to squeeze it in. But you'll notice the gap's bigger. And so it begs the question, which graph, and this is, I suppose, what mathematicians have done over the years. They've said, which graph isn't too low, like this one, and isn't too high, like these ones? And it's no surprise that it's a weird number in between the 2 and the 3, because in between the 2 and the 3, it's either a little bit high or a little bit low. And that weird number that gives you the same gradient as you started with is 2.718 to the x, and that's why we've given it a name. It's y equals e to the x. Now notice this tells us something. It tells us that the gradient of an e to the x graph is e to the x. That's the special thing about this. If I find the gradient of this, now notice something, y equals e to the x. That tells me that dy by the x is going to equal e to the x. And I can go a little bit further. I can say, according to this, that if I get y equals e to the kx, then the differentiation of it, the gradient, notice this notation for the gradient. I'm not sure if you've seen this yet. If you haven't, don't worry about it. I think the book refers to the gradient. The gradient of an e to the kx graph becomes ke to the kx. And this is quite useful information. So let's have a go at this. So it says find the gradient expression of the graph y equals e to the 3.7x. And that's not a very nice function, but notice all it does is it basically says if I want the gradient of this, I've shown you the notation. I don't need to write it yet. So the gradient is just going to be, well, notice this. It says if you find the gradient of e to the kx, it's ke to the kx. So that gives me 3.7 e to the 3.7x. It's that simple. You bring that 3.7 down to the front. Hence find the gradient of y equals e to the 3.7x when x is 5. Okay then, so x is 5. So the gradient, I know the gradient function is this 3.7 e to the 3.7x. So at x is 5, it's 3.7 e to the 3.7 times 5. 3.7 times 5, what's that? That sounds like 18.5 to me. I'll just do it. Menu 1. So 5 times 3.7 is 18.5, that's right. So it's 3.7 e to the 18.5. That's going to be a horrendous number is my guess. Is that what they wanted as the answer? I hope so, because if I type that in, 3.7 times e to the 18.5, I'm going to be, oh well, it's a huge number. I've got 400. 5454.7. That's horrendous. But there you go, that's what they wanted. Exactly the same. Find the gradient expression for the graph y equals 3e to the 2x. Now the 3 doesn't really bother us. The gradient will become, again, notice the bit that bothers me is the fact that it's e to the 2x. So the gradient becomes, bring that 2 down. There's already 3 there, so it's 3 times by the 2. E to the 2x. The power never changes. So that's 6 e to the 2x. Okay, hence find the gradient when y equals 12 again. So I'm doing this. I've got the gradient function at the top. I've got that gradient is 6 e to the 2 times 12, which is 6 e to the 24. Again, I reckon that's quite a big old number. 6. Let's turn my calculator back on. 6 times e to the 24. Oh, it's gone into standard form. Now you either write it like that, or you, it doesn't even say how it wants it. 1.59, 3 significant figures, times 10 to the 11. That might be a better option. It'd be interesting to see what they want in the textbook. So anyway, that's that exercise done. Exercise 8a, page 133. We're just going to play around. I suppose the important thing to remember there is that if we ever get a function y equals e to the kx, then we immediately are able to write its gradient function, not at any point, just at all points, it's k e to the kx. Okay? Good luck with the exercise.